Welcome to the Contaminated Runway Operations lesson. This lesson provides information and guidance for aircraft operations on contaminated runways, including runway surfaces, friction measuring, runway condition reporting, takeoff and landing performance, and operational practices. In recent years, a variety of worldwide regulatory and aviation safety-related agencies have identified runway excursions as a primary safety focus. For example, according to a European ICAO safety report conducted in 2013, at least 2 runway excursions occur worldwide every week. It was also discovered that this rate has not decreased in the prior 20 years. Multiple organizations realized the need for improved policies and procedures in this area, specifically in regards to contaminated runway operations. For the FAA, the catalyst for change began in 2005 with a Southwest Airlines runway excursion during a landing at Chicago Midway. The accident occurred on a December night during a landing on snow-covered runway 31 Center at Chicago Midway. The aircraft overran the departure end of the runway and came to rest in a residential intersection outside the airport perimeter. While there were a number of factors in this accident, the NTSB made the following conclusions related to runway contamination. Guidance on braking action and contaminant type and depth reports would assist pilots, air traffic control, operator dispatch, and airport operations personnel in minimizing the subjectivity and standardization shortcomings of such reports. Establishment of a means of correlating the airplane's braking ability with the runway surface condition would provide a more accurate assessment of the airplane's basic landing performance capability. After the Southwest accident, the FAA formed the Takeoff and Landing Performance Assessment, or TALPA, Aviation Rulemaking Committee, or ARC. The result of this study is Advisory Circular 150-5200-30D, which became effective in 2016. This circular is a comprehensive update to how U.S. airports, carriers, and flight crews deal with snow, ice, and other precipitants in regards to airport operations. These changes are designed to standardize all elements of contaminated runway operations, thereby reducing the risk of runway overrun excursions and accidents. While a portion of the circular is directed at airport operators, this lesson will focus primarily on the information that pertains to flight crews. In 2016, 2 safety reports from the European Aviation Safety Agency, or EASA, and International Civil Aviation Organization, or ICAO, identified runway safety as a major focus subject. From this effort, EASA formed the European Action Plan for the Prevention of Runway Excursions to address the problem. ICAO had already begun adopting policy changes under a Friction Task Force initiative. The FAA's TALPA update, discussed in the previous section, was designed to harmonize with the ICAO changes already being implemented by the initiative. The EASA group has recently proposed rulemaking changes that match both the FAA TALPA updates and ICAO standards. As of 2018, EASA and ICAO still use different reporting systems. There is an expectation, however, that by 2020 they will have adopted the FAA changes. Once this process is finalized, a standardized friction and braking reporting system should be in place that will be consistent to all flight crews, regardless of the country in which they are operating. For now, ICAO standards use a special series NOTAM or SNOWTAM for reporting field conditions to flight crews. This lesson will discuss both the FAA and ICAO reports in detail. Definitions of runway surfaces and contaminants vary between agencies and manufacturers. Select a tab to display the various definitions. Select a tab to display the various definitions. This topic will discuss the different types of contaminants commonly experienced on runways. To begin, contaminants can be classified as either loose or solid. Loose contaminants are surface contaminants that a moving tire will break through. Examples of these include water, slush, and both wet and dry snow. These contaminants can affect the airplane's acceleration and deceleration capability as a result of increased impingement drag and decreased braking efficiency. Solid contaminants are those that an airplane's tire will roll over without breaking the surface. Compacted snow and ice are examples of solid contaminants. These contaminants will not add drag during acceleration or deceleration, but they will reduce braking efficiency due to a reduction in friction. All runway contaminants result in some level of degradation in landing and/or takeoff performance. However, the performance effects vary greatly depending on the type and depth of the contaminant. Each type of contaminant can create its own unique operating environment. Therefore, it is important for flight crews to know the classification of each contaminant, including dry snow, wet snow, slush, compacted snow, frost, water, ice, and wet ice. Dry snow has low free water content, resulting in snow that does not stick together. When making a snowball, dry snow will fall apart. This type of snow normally occurs at temperatures well below freezing. With wet snow, snowflakes are combined with liquid water, allowing it to be easily packed together. This type of snow is great for snowballs. However, it does not contain excess water, and no additional water can be squeezed from it. Slush is water-saturated snow that takes on fluid-like properties. This snow-water mix will displace with a splatter when compressed. Compacted snow has been compressed into a final solid form and will resist any further compression. This type of contaminant will not be affected by aircraft moving over or resting on top of it. If picked up by hand, it will retain its shape or break apart into chunks. Frost is comprised of ice crystals created when airborne moisture comes into contact with a surface that is below freezing. Frost differs from ice in that it is made up of individual, independent crystals, giving it a more granular texture. Water indicates any contaminant in a liquid state with a depth greater than 3 millimeters or 1/8 inch for reporting purposes. Ice is defined as the solid form of frozen water. Wet ice is frozen water that is melting or ice with any discernible surface water. The physical properties and state of the runway itself play a large part in aircraft braking capabilities. We will discuss the following runway properties in the first portion of this topic: runway texture, drainage, and maintenance. The remainder of the topic will discuss general runway design elements. The texture of the runway surface has a considerable effect on friction, particularly when the surface is wet. Surface texture can be expressed in two different categories: macro texture and micro texture. The macro texture component of the runway surface is dictated by the size of aggregate used during construction. It is the visible roughness on the pavement and is possible to gauge with the naked eye. In both wet and dry conditions, macro texture is the primary factor for braking at higher speeds. Microtexture is the physical texture of individual surface stones. Too small to be discerned by the naked eye, microtexture is gauged by touch rather than appearance. Microtexture is a primary component of braking at slower speeds. The microtexture runway component has little effect in wet conditions at higher speeds. Runway drainage serves to minimize standing water by removing it from the wheel path. Adequate drainage is primarily achieved through proper design of runway slope and camber. This helps prevent precipitation from pooling in the primary operating zone of the runway. Special surface treatments, such as grooving and a porous friction course, can help drain water via surface voids. Runway grooving provides a method for removing water from the runway. Without these channels, the water runs the risk of forming a thin surface layer, which could result in hydroplaning. Grooving depths may vary based on country. ICAO rules specify that grooving standards are set by each applicable state regulatory agency. Another method of runway surface design is porous friction course, or PFC. PFC is an open graded asphalt mixture poured over a normal concrete surface. PFC asphalt features interconnected air voids that allow rainwater to drain away from the surface into the pavement. This results in a significant improvement to friction characteristics. Both grooved and PFC surfaces offer substantial benefits while operating in wet conditions. Runways that are grooved or include a PFC overlay will normally be noted as such on airport facility directories or Jeppesen approach charts. Maintaining the runway to certain standards ensures that the best possible friction can be attained for the given conditions. Runway maintenance includes long-term projects such as regrooving or rubber removal, and short-term tasks such as snow removal during inclement weather. Airport operators are expected to maintain the airport movement area to a no worse than wet condition during winter storms, if possible. The operators use high-speed rotary plows, snow plows, solid and liquid material spreaders, runway brooms with air blast, and carrier vehicles to attempt to maintain a status of no contamination accumulation. To reduce the chances of incursions, crews should familiarize themselves with the most up-to-date NOTAMs to determine where snow removal activities are taking place. It is important to understand the terminology for runway elements that are relevant to stopping and overruns. The stopway is an area beyond the takeoff runway that is as wide or wider than the runway and centered upon the extended centerline. It is able to support the airplane during an aborted takeoff without causing structural damage to the airplane. The stopway is designated by the airport authorities for use in decelerating the airplane during an aborted takeoff. The clearway is an area beyond the runway pavement under the control of airport authorities. Within this area, terrain or fixed obstacles may not extend above specified limits. No fixed or movable obstacle should penetrate the clearway during aircraft operations. The runway safety area is an area around each runway that is prepared or suitable for reduced aircraft damage during an excursion. There are no performance considerations for the runway safety area. This area surrounds the runway, with dimensions ranging from approximately 35 to 150 meters, or 120 to 500 feet wide, and extending between 70 to 300 meters, or 240 to 1,000 feet, beyond the runway end. Regulations state that safety areas must be capable, under dry conditions, of supporting snow removal, aircraft rescue, and firefighting equipment. They should also support the occasional passage of aircraft without causing major damage to the aircraft. No objects should be located in the safety area except those required for normal airport functions. Any required objects, such as approach lights, should be constructed on frangible structures of the lowest possible height. An engineered material arresting system, or EMAS, may be installed at the end of some airport runways. EMAS uses crushable material that aircraft tires will sink into, creating a strong deceleration force to slow down and stop the aircraft. This technology improves safety at airports where it is not possible to have the standard 300-meter or 1,000-foot safety area. As discussed in the history topic, there is a major effort underway to standardize runway friction assessments and how that information is disseminated to pilots. However, depending on where you operate, some differences in reporting may still exist. For runway conditions in the U.S., the FAA will issue field condition NOTAMs or FICONs. ICAO, however, still uses a special NOTAM called a SNOWTAM. Although the information given is essentially the same, there are some format differences between the two, which will be discussed in this topic. In general, no matter where you are operating or what type of report is given, crews should remember the following. There is no acceptable method for correlating airport friction measurements to the airplane's braking capability. Runway friction readings are not a guarantee for actual aircraft braking performance. And always use your best judgment and err on the side of safety when calculating landing or takeoff distances. As part of the TALPA updates, the FAA has aligned with ICAO verbiage regarding braking action. Fair is no longer used and will be replaced with medium. ICAO may still use the term less than poor to indicate the lowest level of friction. Braking action terms include the following from best to worst: good, good to medium, medium, medium to poor, and poor. It is important to understand that using a phrase such as good to medium indicates a braking value between good and medium. It does not indicate braking action along the runway length that changes from good to medium. That being said, reports may be given for individual fractions of the runway as applicable. Specific guidelines for each level of braking action are as follows. There are two types of friction measuring equipment: decelerometers and continuous friction measuring equipment, or CFME. Decelerometers are recommended for airports where longer runway downtimes are unacceptable, or where it is difficult to gain access to the full runway length because of another crossing runway. Electronic decelerometers automatically compute and record friction data for each third of the runway. They also provide a printed report of the friction data. Mechanical decelerometers may be used as a backup. However, this type does not provide automatic friction averages or a printed report. Continuous Friction Measuring Equipment, or CFME, is either attached to a trailer or attached to the rear axle of a vehicle. Each machine skids a special non-treaded tire across the pavement surface. The resultant resistance force is measured to calculate the surface frictional properties. These units provide a continuous graphic record of the pavement surface friction characteristics, with friction averages for each 1/3 zone of the runway length. CFME devices are recommended over decelerometers for measuring friction characteristics of pavement surfaces covered with contaminants. The new FAA TALPA procedures utilize a runway condition assessment matrix, or RCAM, to assess runway conditions. Although the RCAM is primarily used by airport operators, flight crews should be familiar with what it is and how it is used. The goal of the RCAM is to assign each runway third a runway condition code from 0 to 6. These codes are the new objective standard for expressing friction values for a given segment of the runway. To use the RCAM, airport operators assess the runway for the type and amount of precipitation that exists. If less than 25% of the runway is contaminated, a runway condition code will not be issued. In this case, the contaminant type and coverage for each third may still be reported in a FICON and distributed for pilot information. In this example, 20% of runway 9 at Kansas City International Airport has been observed to have 1/8 of an inch of slush. If more than 25% runway contamination exists, the type and depth of contaminant for each runway third is noted. Using the left two columns of the RCAM, a runway condition code is then assigned for each third of the runway. If the airport operator believes these runway condition codes reflect the runway condition, no additional assessments or adjustments are required, and these codes are distributed via FICON or other means. If additional assessments or observations indicate a worse runway condition, the airport operator may downgrade the runway condition code using the RCAM downgrade assessment criteria. These criteria include friction readings, referred to as the coefficient of friction, or mu value, from an authorized vehicle, vehicle deceleration or directional control observations, and pilot reports. The criteria in these columns may be used only to verify or downgrade the existing runway condition codes. They cannot be used to upgrade them. There are instances where a 0 or 1 may be generated by the RCAM in conditions that may not be as slippery as indicated by the runway condition code. In these circumstances only, the operator may upgrade the runway condition code up to but no higher than 3, if the following conditions are met. All observations, judgment, and vehicle braking support the higher runway condition code. Mu value readings are 40 or higher. And the operator continually monitors the runway condition using all possible assessments to ensure the condition does not degrade. The new TALPA directive and runway condition codes have affected changes to how field condition NOTAMs are formatted. Let's look at a couple examples. Notice that both NOTAMs include the FICON header, making them easier to find when many NOTAMs exist for an airport. Each begins with an airport code and runway observed. Runway condition codes are then listed in order of touchdown, midpoint, and rollout. In the first, Kansas City is reporting different runway condition codes and conditions for each third of runway 9. After that, the coverage of each third, as well as the depth and type of contaminant, is listed. In Bradford, the entire runway's condition code is 3, and the runway is 100% covered in a 1/4 inch of dry snow over compacted snow. The FICONs end with an observed time and a valid time range. The format for these is year/month/day/time. In Bradford, for example, it was made March 15th, 2018 at 14:57 Zulu. FICONs are normally valid for 24 hours, as seen by the valid time ranges here. Some airports, particularly smaller ones, may not always be able to monitor weather conditions due to staffing limitations. In this case, a NOTAM should be issued with the text, "Airfield surface conditions are not monitored between the hours of X and Y." The phrase "airport unattended" is no longer used in this context, as it gives the impression that other airport services are unavailable or inaccessible. If no surface observations will be made for more than 24 hours, a single NOTAM with the phrase "surface conditions not reported" should be issued. For states that have not adopted the updated FICON NOTAM format, a special series NOTAM, or SNOWTAM, is used. ICAO defines this as a notification of the presence or removal of hazardous conditions due to snow, ice, slush, or standing water associated with snow, slush, and ice on the movement area. SNOWTAMs feature a specific coding system that is unique to this type of report. Each field is preceded by an identifier, such as A, B, and so on. Field A displays the airport code. Field B shows the time of observation using the format month, day, hour, minute. Field C indicates the runway observed. This is always indicated by the lower of the two reciprocal runway numbers. Fields F, G, and H indicate the actual contaminant data for each third of the runway, separated by slashes. F shows the type of contamination using the following codes. If two numbers are displayed, it indicates one type of precipitation on another. A code of 4-8, for example, indicates dry snow on top of compacted snow. Field G indicates the depth of contaminant in millimeters. If the depth cannot be ascertained, it is shown as a double X. Field H shows the braking action or friction value, either as measured or estimated. Measured values are shown as a double-digit number using the following table. Estimated values are single-digit and use the following data. Field H may also include a code indicating the type of equipment used for friction measuring. Fields N and R indicate the conditions on the taxiways associated with the runway and the apron, respectively. Finally, Field T is an open text field for any notes or relevant information. As with FICONs, the maximum validity of a SNOWTAM is 24 hours. In addition to FICONs and SNOWTAMs, pilot reports from other aircraft can provide valuable data on actual existing conditions and their effect on performance and braking. Landing crews can inform ATC on the quality of braking by giving a braking action report. During inclement weather, ATC may sometimes query a landing aircraft for a report. Crews should do their best to be ready with braking information when exiting the landing runway. The crews giving braking action reports should indicate where the condition was encountered. For example, Flight 129, braking action poor first half. ATC will, when applicable, furnish these braking action reports to all landing aircraft. In addition, ATC will report the type of aircraft that furnished the report, if known. Flight 908, runway 14, braking action poor first third, fare second third, as reported by a 757. This provides a more accurate representation of the conditions to other aircraft. When considering pilot reports, keep the following variables in mind: the time it was reported, the rate of precipitation, and the reporting aircraft type. A braking action report from a small, light aircraft may not be relevant to a large transport category airplane. This topic will discuss some of the impacts contaminated runways have on takeoff performance, as well as best practices for these conditions. Remember, the best and most relevant information for operating on contaminated surfaces will always be found in your aircraft-specific manuals. It is imperative for crews to be familiar with these specific operations and to know where to find them for reference during adverse weather operations. Contaminated runways can affect takeoff performance in two distinct ways: increased drag, causing an extended takeoff distance, and reduced braking effectiveness during a rejected takeoff. Rejected takeoff performance is calculated as an accelerate-stop distance. This is defined as the distance required to accelerate to VEF, experience a failure of the critical engine, then bring the aircraft to a complete stop. When calculating accelerate-stop distances for a wet runway, credit for available reverse thrust may be included. The accelerate-stop distance is frequently the most restrictive performance constraint when operating on contaminated runways. Assuming a constant aircraft weight, using a lower V1 speed can reduce the accelerate-stop distance by shifting the point at which a takeoff would be rejected to earlier in the takeoff roll. This lower V1 allows the aircraft to accelerate and stop in a shorter length. However, lowering V1 adversely affects the engine-out accelerate-go distance. If V1 is reduced, a longer portion of this theoretical takeoff is conducted with one engine inoperative, resulting in a longer required field. The best performance is found where the accelerate-stop distance equals the engine-out accelerate-go takeoff distance. The V1 speed for this point allows for the best accelerate-stop distance while meeting the requirements for a takeoff with engine failure at V1. Due to takeoff distance requirements and altitude allowances, there may be times when dry runway performance is more restrictive than wet runway performance. When calculating takeoff performance for contaminated runways, flight crews should compute performance for both wet and dry runways, then use the more restrictive of the two. When performing a takeoff on a contaminated runway, the following techniques and practices will allow for the greatest margin of safety. Reduced thrust takeoffs using assumed temperature or engine derates should not be used for takeoff on standing water, snow, or slush. Most performance programs will allow reduced thrust operations if the runway condition is wet. Using the RTO setting on Autobrakes, if installed, eliminates any delay in braking when the thrust levers are moved to idle. This is especially critical during higher speeds, when timely brake application is necessary for a successful abort. On slippery, contaminated runways, the flight crew should make every effort to set engine thrust symmetrically to ensure directional control is maintained. If, for any reason during the takeoff, directional control is in doubt, the takeoff should be promptly rejected. Landing on contaminated runways presents unique challenges and performance considerations. Crews that assess and plan for adverse runway conditions will be much more likely to execute a safe landing. The stopping forces involved with contaminated runways differ from those on dry runways. Although braking efficiency is reduced on contaminated runways, there is an added benefit for rolling drag, which is created when contaminants impact any part of the aircraft structure. Total stopping force is the combination of rolling drag, aerodynamic drag, reverse thrust, and braking. When landing on a contaminated runway, reverse thrust is normally the dominant initial deceleration force. As aircraft speed decreases, the effectiveness of the wheel brakes increases. This increase normally occurs at roughly the same speed at which thrust reversers will be moving to the stowed position. This highlights the importance of timely application of reverse thrust, the most effective tool to slow the airplane into the region where wheel brakes effectiveness increases. In the case of the Southwest runway overrun in Chicago, the delayed deployment of thrust reversers was listed as a major factor in the accident. Although specific regulations may vary depending on country of operation, in general, air carrier flights must prove adequate landing performance exists before departure. Required landing distance is derived from actual landing distance. Required landing distance is calculated for a dry runway by adding a factor of 1.67 to the actual landing distance. For a wet runway, a factor of 1.92 is used. The higher adjustment factor for a wet runway creates a margin of safety for a landing that may include less than ideal braking. However, some regulations allow the larger wet runway factor to be waived if the aircraft's flight manual includes landing performance data specific to wet runways. Required landing distance is calculated before departure and is only meant to satisfy the regulatory requirements for landing distances. Actual stopping performance will vary based on many factors, including the type and amount of contamination on the runway. If, during flight, destination field conditions are reported to be contaminated, flight crews should make every effort to calculate updated landing performance for the existing conditions. For all aircraft and conditions, the following performance guidelines should be observed. Performance data in your company aircraft manuals, AOM or QRH, or onboard performance system are the final authority on landing runway requirements. Performance data may or may not give credit for reverse thrust. Be aware which is the case for the data you are using. If conditions vary along the runway length, use the most restrictive when calculating performance. And always be aware of aircraft MEL items or non-normal conditions that will result in a performance penalty. Some example MELs that might result in a performance penalty include, but are not limited to, anti-skid, auto brakes, spoilers, and thrust reversers. If in doubt regarding performance data, aircraft assumptions, or performance impacts of inoperative equipment, consult your manual or dispatch facility. If the aircraft is equipped with auto brakes, manufacturers recommend their use for landings on contaminated runways. The performance benefits of auto brakes include Brakes are applied earlier in the landing roll. Brake application is generally more efficient than manual braking. And for some aircraft, brake pressure automatically compensates for the impact of rudder input imposed by crosswind side loads. The crew should select at least the lowest level of auto brake required by performance calculations. If a higher setting is desired, that may be used. Full braking performance will be applied on wheel spin-up after touchdown. It is imperative that if the auto brakes do not engage upon touchdown, the pilot flying applies manual braking immediately. Hydroplaning occurs when a tire experiences partial or total loss of contact with the pavement. Hydroplaning can occur during landing or takeoff. There are 3 types of hydroplaning: dynamic, viscous, and reverted rubber. Dynamic hydroplaning occurs when there is a film of water that is at least 2.5 millimeters or 0.1 inch on the runway. As an aircraft moves over the runway, the force of the tire on this water increases its pressure. When the water pressure equals the weight of the airplane, the tire is lifted off the runway surface and stops rotating. Both directional control and braking effectiveness are lost. Viscous hydroplaning can occur on very thin films of fluid that lie on a smooth surface. Fluid depth as thin as 2.5 millimeters or 1/1000th of an inch can create conditions for viscous hydroplaning. This type of condition can feature the same friction coefficient as wet ice and can occur at much slower speeds than dynamic hydroplaning. Reverted rubber hydroplaning occurs during heavy braking that results in a prolonged locked wheel skid. Only a thin film of water is required on the runway to facilitate this type of hydroplaning. Skidding results in heat buildup, which melts the rubber surface of the tire. The melted rubber acts as a seal between the tire and the runway. The heating converts the runway moisture into steam, which supports the tire off the runway. The degree of hydroplaning depends on the following factors: absence of runway surface roughness and inadequate drainage, depth and type of contaminant, tire inflation pressure, ground speed, and anti-skid operation. The best practice for avoiding hydroplaning during landing is to conduct a firm touchdown. During the landing phase, the flying pilot should make every effort to touch down firmly and with minimal flare. Landing in the first part of the runway allows deceleration to occur sooner, thus reducing the runway distance required for landing. There have been instances where landing softly on a contaminated runway resulted in the aircraft's air-ground logic not transitioning to ground mode. In this case, ground spoilers, auto brakes, and reverse thrust are not available. A firm touchdown helps ensure the aircraft transitions to the ground mode. Once the main gear is on the runway, the nose wheel should be lowered as soon as possible. Lowering the nose wheel sooner has the following benefits. It assists in maintaining directional control. It decreases wing angle of attack, reducing lift and transferring load onto the main tires. And it increases contaminant drag. Braking technique during landing differs depending on the availability of an anti-skid system. For aircraft with anti-skid inoperative or not installed, brakes should be applied progressively throughout deceleration. The pilot flying should recognize the point at which skidding occurs, then reduce brake pressure until the skid stops. The highest braking efficiency will occur at the point of maximum application just before wheel skidding begins. Be aware that skidding is much more likely at higher speeds and may not be immediately noticeable when it is happening. For aircraft with operable anti-skid, the brake should be applied firmly and consistently throughout the deceleration. Maximum braking efficiency is reached when the brakes are fully applied and held, allowing the anti-skid system to operate. Reducing brake application or cycling the brake pedals will defeat the purpose of anti-skid and will adversely affect landing distance. As the anti-skid system modulates brake pressure, a pulsing sensation will be felt. This is an indication that the system is operating normally. Most transport category aircraft will have MEL relief for operating with inoperative anti-skid systems on wet runways. When applying this MEL, it is important the crew be familiar with and follow all operational notes. Typical notes may include: operations must take place on PFCO or grooved runways. All reversers must be operative. Approved performance data is available and used. And stricter crosswind limitations. All deceleration devices on the aircraft should be utilized as soon as possible after touchdown. For the crew, this means immediately deploying thrust reversers to the maximum position, ensuring autobrakes, if used, are operating normally, and ensuring spoilers have extended. If it is observed that the autobrakes have not engaged, the crew should immediately apply maximum manual braking. Similarly, if the spoilers do not extend automatically, they should be manually moved to the up position. During the landing rollout, it is recommended that nose wheel tiller steering is not used until the aircraft is at or below taxi speed. This reduces the possibility of nose wheel skidding and loss of directional control. After landing or operating on runways contaminated with ice, slush, or snow, it is recommended that crews examine the following aircraft areas for contaminants: underside of flaps, gear struts, brakes, wheel wells, antennas, and other sensitive areas. Ice or other contaminant buildup in these areas may adhere to the aircraft and may not be removed during a future de-icing. This could pose a safety threat for the aircraft's next flight. Be aware that some aircraft AOMs require the flaps to be left extended after landing to facilitate this inspection.
That is incorrect. That is correct. That is incorrect. That is incorrect. That is correct. That is incorrect. That is incorrect. That is incorrect. That is incorrect. That is incorrect.